So I'll embarrass Pedro a little bit. He doesn't need an introduction, of course, but this is our 2021 Service to the Community winner. Take it away, Pedro. You should have control.
Thank you, Tom. I guess you guys can hear me.
Yep, sounds good.
Cool. Okay, so I'll talk about user-defined output functions. And the motivation for this is very simple. It's really cumbersome to introduce a new output in SU2. You may find yourself changing things in the config, in the solvers, in the output classes, and then on the optimization scripts that you're using. But it's of course very useful to be able to do this type of thing. So it reduces code bloat by not having to introduce a bunch of functions that then all the community needs to carry. It lets you do clever things for optimization like constraint aggregation or weighted objective functions. And so it's just the type of thing that leaves you with the question, how hard can it be to just implement something like this? So just being able to write some string with the variables that you want to, with some expression of the solver variables or of other outputs, and just compute some area averages, mass averages, and so on. And then once you have your custom output, use that in an optimization by using it as the custom objective function. The most of the talk will be answering the question of how hard can it be, and I'll give a somewhat advanced example of this being used. So I'll do a constraint optimization with an exterior penalty method, and in this strategy, you should only require one adjoint solution per primal solution used to compute the objective, which in this case is drag. But also because you're lumping all your constraints together with this, you still only need one adjoint per operating point. So that's what I'm doing here. I'm computing this penalized objective function with drag, and then a penalty on lift and a penalty on pitching moment. And so this should run with this will run with only one adjoint solution, since we're putting everything together in the same objective function. And so this I will obviously use everyone's favorite subsonic airfoil, NACA 012, but put it at transonic speeds, and then minimize drag with a lift constraint and a pitching moment constraint, and also two geometric constraints, one on the cross section of the airfoil and the other one on the thickness. And this is the FFD box being used to manipulate the geometry. Right, so shopping list for what we're trying to implement. We need some way of converting the expressions into C++, some things that can be evaluated with the values we currently have in the code. So replace the variable names with their actual values. Then we need some internal representation of these custom outputs. We need to implement whatever built-in functions we support, so area averages, mass flow averages, and so on. And we need some way of mapping variable names, such as velocity x, to actual code. And in the code, we know where to get velocity x, but we obviously don't want the we obviously don't want to write something ugly like this in the config, because to write that, you might as well just write C++. So for the first part of taking strings and converting into something that can be evaluated, I wrote this very simple math expression library. And basically what it does is takes a string and then splits it by operators and functions until you end up with some tree that looks like that. So if you were to compute this, you could think that you would do power of C square, and then times m with the result of this. But this is not stored like this because that's not that efficient. So this is actually stored as a list of symbols, and then as a very small table where we store the node, we store the type of the node. So this can be either the operation times power plus minus so on. We store or if the node is actually a symbol like C or M, or if the node is actually a constant like this 2 here. And then the way to evaluate something like this is to just start bottom up. And if we get to a constant, you immediately know what the value is because you stored it while you parse the string. If you get to a symbol, then we need some way of going or of getting the value, the current value for this symbol. And so this is the role of the user to provide some object that maps these indices and therefore symbol names to symbol values. And if you get to a mat function type of node, you know what are the children of this node. So for example, here this power as a left children 3 and a right children 4, and so you just the implementation of the library knows that it should take whatever value it got for 3 and raise it to whatever value it has on node 4. So that's how that bit works. Then we need some internal representation of custom outputs. And this will serve as also to document a bit what was implemented in the code. So there's basically a struct in C output, which is this custom output, which just stores the name, the type, and the expression of, and this is also where we define the types of available built-in functions. And then there's a function also of C output that parses this syntax of name, colon, type, expression markers. And if you're wondering where the choice of tokens came from, so if you're wondering why I've used colon instead of equals, is because equals is already used for all the other config options. And parentheses was kind of ambiguous because parentheses you can use on the expression itself. So this makes it a lot easier to just break this thing into chunks. That's where the syntax came from. So there's this function that takes that raw string in the config file and creates just a vector of these custom outputs. On that note, the available built-ins we have right now are a macro, and macro is basically just a string that is replaced where it occurs in other custom outputs. So this does not create a new output by itself. It's just a mechanism to save typing. So yeah, if you know me, I don't like to duplicate things. Then there's a function, and function is an expression of other scalar outputs, but of course cannot use solver variables because those are kind of fields. And then we have area averages and mass flow averages that compute, either one or the other over a list of markers, and this can operate on solver variables and will give you a scalar quantity. And then we have area integral and mass flow integral, which is basically same as above, but an integral instead of average. The macros are handled by which is meant find and replace while parsing the custom outputs immediately, and the others are currently implemented in CFlow output set custom outputs. So only the flow solvers have this functionality so far. The kind of challenging aspect of this is actually to map variable names to code. So the expression library extracts the symbols, the variable names, from the expressions and then asks for a value for the index of each symbol while we're evaluating the expression. For outputs like, for history outputs like drag or lift, we can easily look up the memory location of where we are storing this value in the output, since we have this output maps, and then we can easily associate the pointer to this value with the index that the expression library wants to use. However, we don't have a functionality like that for solver variables, and these mel indices are based on just on the order that the symbols are found in the expression, and so they do not map directly to the primitive indices or the indices of variables of other solvers. And we also need to handle variables of other solvers. And so just as a note, if you're wondering why are we dealing with indices and integers and not just with the names of things, it's of course because that's really slow if you are evaluating this expression once per vertex of the markers where you're computing an average, for example. So the idea is always to take strings out of the way and replace that with some code that is more efficient. Before we go any further, we can check live on how the optimization is going. And by the 10th iteration, we have 2 shocks instead of 1. So I think things are going pretty well. So continuing on the problem of mapping variables to code. We need another layer where we take the symbol index that we got from parsing the expression to some other integer that encodes whether this symbol is an output or a solver variable. If it is a solver variable, what solver does it correspond to? So is it from the flow solver? Is it from the turbulence and so on? And also possibly the variable type, because each solver can have as different quantities, as you know, conservative, primitive, and so on. And so we need the type of, we need to know where we want to read it and also some index. And this is done in this cflow output, convert variable symbols to indices. And it's basically something silly like if it is a variable, the code is the solver index times a constant. And this constant is basically picked as maximum reasonable value of number of variables that the solver can have, plus the variable index. And for obvious reasons, this maximum variables is a power of 2. If it's an output, then we just give it some other constant, not a variable, which is basically larger than anything that can occur on this branch here. And the output index, and here output index is just used to access the pointer to the output value. And these are the variables that are covered in the implementation right now. So it's all the flow solver primitives and also the turbulence variables, which are just referenced in this way if there's more than one. So turb square brackets 0 to access the first one, square brackets 1 to access the second variable. Same for radiation and same for species. And so we end up with these codes, with one of these codes stored for each index that is associated with a symbol of the expression that was parsed by the library. And this is stored in the custom output struct. So then when we eventually want to evaluate the expression where we evaluate it inside custom outputs, we need to create we have to create a custom way of doing this per point as we are looping over the vertices of the marker. So there's this functor that takes the code that we've generated before and then does the reverse process of Is it a variable? If so, extract the solver index and the variable index. And then if it's the flow solver, for example, we want to look at primitives instead of looking at conservatives. Otherwise, if it's another solver, we look at the conservatives, let's call it. And if it's not a solver variable, it's an history output. And in that case, we know that we stored a pointer for that directly, and we can just go straight to that pointer to get the value. And so in the end, this is fairly efficient. So for for a handful of custom functions, the cost of this is similar to using marker analyze, which is about 1% of the time per iteration. So actually the major inefficiency is not the expressions. It's that this is implemented as computing one expression at a time, which involves going over the data multiple times. But that was kind of a requirement to be able to use the result of an expression on a subsequent expression. So there's of course clever optimizations we can do there, but at the moment it's pretty good. So you might be wondering how to extend this to other variables or other physics. And to cover more variables like geometry would simply require creating some integer code for them. So you could imagine, for example, having a dummy solver index for the geometry normals, and then handling this in that functor thing in a very similar way to what was done. So if the solver index is equal to this dummy solver index for geometry, you would know that you'd need to go to the normal vectors instead, or to the coordinates, and so on. And alternative, if this gets complicated, we can also just store this a triplet of values instead of lumping all together in just one integer. So you could have like 3 values that would tell you if it's an output or a geometry thing or a solver variable, and also the solver index and the variable index. Extending for other physics like solid deformation would require specializing the conversion of the variable symbols to indices, and also specializing the function that is computing the outputs by looping over the markers. Because if you're looking at other physics, you probably also want to decide what built-in functions make sense for that. So you probably don't want to do a mass flow average on a solid deformation problem. Okay, so a short few minutes later, we went from a NACA 0012 to a Ray 2822-ish looking airfoil. So the shock is not as ugly anymore, and we met our constraints as we were expected to, and minimized drag as we were expected to. So it works, and we did this with only one adjoint per iteration. Of course, we also did a lot of iterations, but that's a different problem. Yeah, that's it. We have user-defined output functions. I think they're easy to use. People will let me know, hopefully. They're not too slow, and they're compatible with discrete adjoint solvers, which means you can use them for whatever optimization purposes you want. Thank you.
Okay, thanks, Pedro. So my nerdy joke was going to be, I appreciate you overlapping your communication and computation. So nice talk. Any questions? We're a little bit late for break, but let's see if anybody in the audience wants to. Yeah, we have a couple.
I've been looking forward to seeing anything like this in the SU2 world. Is this already
Yes, this is a question from Everett asking if this is already in development.
This is released, version 7.4.0.
Great. Another question from Toby up front.
Yeah, well, thank you for my side. I think it's a great feature comparable to the CLX experiment, which I was always looking online. You talked about the performance applications and how the source terms are primary conditions, so not as an output part of the overall, within the loop of the whole.
Yeah.
So is there something that's holding us back from basically putting a lot of stuff into the just making everything through the
Okay, so let me paraphrase the question, Pedro, in case you didn't hear. Toby says, thanks for the talk, and it looks a lot like UDFs or an expression language. And so his next thought is, why not use this for source terms, boundary conditions, stuff that's in the inner loop? So the question is, what's stopping that? Could you use this, and do you plan to?
It's doable, but for things like that, I think we should actually go the Python wrapper way, because for some things that's already there, and it would be more versatile / more efficient. But it would be doable. It would just be more work, and you would probably want a more featureful language, let's call it, to do that type of thing, because the expressions right now is just basically pair view calculator type of thing. So it might not be. Yeah, you'd probably want something that would allow you to do dot products of geometry quantities, for example, instead of having to write x times x plus y times y plus. Yeah, so Python would be my answer for boundaries and source terms.